go a little further to try to put resonances in a more intriguing footing, and that you can play with them if you're at some point interested. So let's think of the scattering amplitude that we had. We had AS. Remember, the scattered wave was AS e to the I kx. Yes, that direction. And what was AS? Well, AS squared is sine squared delta. So if you remember, this was sine delta e to the I delta. So let's stick to that and try to write it in a funny way. Certainly, AS is becoming large near resonance. So let's think when AS becomes large. Well, in another way, let's be a little creative about things. It's good sometimes not to be too logical. So let's write this as sine delta. I'll do it here. Sine delta over e to the minus I delta. And that's sine delta over cos delta minus I sine delta. That's all good. AS. Let me divide by sine delta both sides, both numerator and denominator. So, no, I divide by cosine delta. So I'll have tan delta over 1 minus I tan delta. I divided by cosine. Okay. You want AS large? You really want it large? Choose tan delta equals to minus I. Sounds crazy. It's not really crazy. The reason it sounds crazy and it's somewhat strange and not very logical is that tan delta is a phase, and the tangent of any phase is never an imaginary number. So then I would have to think of delta itself as a complex number. And what would that mean? So things are weird. But it's certainly the fact that AS will become infinite, not just large, but infinite. AS will become infinite. And you say, well, this doesn't make any sense. But maybe it makes sense in the following way. This is the line of real phase shifts. Values are real. And here is the world of complex phase shifts. These are the real phase shifts, and there are the complex phase shifts. Maybe if the phase shift becomes infinite off the real axis, it's just large on the real axis. So actually, if you wanted it to be very large, you would have to get off the real axis. If this sounds vague, it is still vague, but in a minute it will make it precise. So I suggest that we take this idea seriously, that maybe this means something, and we can try to argue that by looking back at what resonances do. So So what I will do is look, we've modeled a resonance here, tangent delta. So let's look at what AS does. We have it there. AS is tan delta. Well, tan delta, we had it in the middle blackboard, is beta over alpha minus k. 1 minus I beta over alpha minus k again. So that's how AS behaves in general. That's fine. There's no, at this moment, there's nothing crazy about this, because this is something you all agreed. Nobody complained about this formula. So AS is given by that formula. That's also legal math so far. So we'll have this. And then let's simplify it a little bit. This is beta over alpha minus k minus I beta. So this is still beta over alpha minus I beta minus k. So, okay, we usually would plot AS as a function of k. That's what we're trying to do. It's a function of k. And now here is the formula for AS as a function of k. And here is k. But let's be daring now and not say this is k. This is the complex k-plane. And yes, you work with real k, but that's because that has a direct physical interpretation. But maybe a complex plane has a more subtle physical interpretation, and that's what I claim is happening here. This quantity becomes infinite near the resonance. Here was the resonance, what you call the resonance. But this becomes really infinite, not at alpha, when k is equal to alpha, but when k is equal to alpha minus I beta. Beta was supposed to be small for a resonance, so here is minus I beta. And here is this very unusual point where the scattering amplitude blows up. It has what is in complex variables, if you've taken 1806, it's called a pole. In a complex variable, when you have a denominator that vanishes linearly, you call it a pole. Things blow up. So the scattering amplitude has a pole off the real axis, and the interpretation is correct. At this point, this function becomes infinite. And what is happening on the real line, that AS is becoming large, is just the remnant of that infinity over here that is affecting the value at this point. So in the complex plane, you understand the function a little better. You see why it's becoming big, and you can see also with a little analysis why the phase is shifting very fast, because you have this quantity. And that's called the resonance. And this is the mathematically precise way of searching for resonances. If you want to search for resonances, what you should do is you have your formula for delta as a function of k. And it's a complicated formula, but now try to solve the equation tan delta of this is equal to minus I. Because that's what guarantees that you have a pole that indeed it blows up at some value. That's where AS blows up, which we see directly here. It's this value, alpha minus I beta. So alpha minus I beta is a pole of AS. And therefore, it must be happening when tangent of delta is equal to minus I. So you have a very complicated formula maybe for tangent of delta. But set it equal to minus I and ask Mathematica to solve it. And a number will come, K equal, or Ka equal 2.73 minus 0.003 I. And you will know, oh, that's a resonance. It's off the axis. And the real part is the value of alpha. And since this is beta, the closer to the axis, if you find more, the more resonant it is. And by the time it's far from the axis, some people call it a resonance, and people say, no, that's not a resonance. It's a matter of taste. But there are important things, which are these poles. So I will not give you exercises on that, but you may want to try it if you want to have some entertainment with these things. I want to say one more thing about this, and it's the reason why this viewpoint is interesting as well. We already found that if we want to think of resonances more precisely, we can think of them as just an equation. You solve an equation and it gives you the resonance. And this is the equation you must solve. And you must admit complex K. But now you can say, look, actually, you have E is equal to H squared K squared over 2M. And, okay, we have real Ks. This is the physical scattering solutions. Complex Ks, those are resonances. How about imaginary Ks? If K is equal to I kappa, if kappa belonging to the real numbers, then the energy becomes minus H squared kappa squared over 2M, and is less than 0, and it could represent bound states. So while you began with scattering solutions of real K representing your waves, now mathematically you're led to resonances understood as poles in the scattering amplitude here. We see that K's in the imaginary axis would represent bound states. So the complex K plane is very rich. It has room for your scattering solutions, it has room for your resonance, it even has rooms for your bound states. They're all there. That's why it's a valuable extension. I have not proven for you that bound states correspond to poles, but it's a simple calculation, and that I will assign it for you with a little bit of guidance. And you will see that also for the case of bound states, you get a pole in the scattering amplitude, and that will complete the interpretation of that. Now people go a little further, actually, and they invent poles in this part, and they're called anti-bound states. And you say, what's that? If you have a bound state, you match a solution to a pure decaying exponential in the forbidden region. In an anti-bound state, you match your solution to a pure increasing exponential, a pure one. Does that have an interpretation? Actually, it does have Some nuclear states are associated with anti-bound states. So So the mathematical description, the rich complex plane is ready for you if you just do scattering amplitudes K, resonances complex K, normal bound states imaginary K positive, anti-bound state negative K. It's a nice start.